So now we're going to talk about the Taylor-Maclaurin series. So there's actually quite a few definitions. Some of them they already know, right? But we're basically still focusing, excuse me, I just read on there, on how to solve. We're basically using series and general to basically solve integrals or derivatives, right? So at first we're going to start off kind of easy, then it kind of gets more complicated. But I actually think this is a little bit easier than last time, all right? So just a little reminder. Just a little reminder that this is what power series is, and this is the Taylor series. And then when they talk about the Maclaurin series, is basically a Taylor series that starts at its center as z is equal to 0. Okay, so just FYI. Now, in general, guys, you really are going to have to remember, and they're like the first 3 questions on your homework, 4 questions, I think. You're really going to have to remember a lot of these that I told you from before when we were doing Taylor polynomials. For example, you should know that e to the x, you have a series that will be the same, which is this one. Okay, so now, since I know that's what that is, okay, and in general, this would be, if you start plugging in a 0 for n and so on and so forth, you get 1 plus x squared over 2 factorial plus x3 over 3 factorial and so on, right? Now, the reason that's important is because now when we're trying to use a Maclaurin series for this, well, here's my Maclaurin series for e to the x, okay? So all we're going to do now, okay, is basically we are going to say that e to the negative 2x is going to be the same thing as this series right here, except for now, I'm going to replace this x that's right here. I'm going to replace this x right here. This in this series, I'm going to replace that with a negative 2x. And notice that nothing else changes in that. Okay, that's about the only thing that's different. And of course, we could rewrite that, and we probably should, just because when it's an alternating series like this will change some things for you. So I normally tend to factor out the negative 1, and I write that as a negative 1 to the nth power. And I just write basically the rest as 2x to the n power. I just found that that's a little easier for me to actually find out the terms, but anyway. All right, so that's the rewritten version. And then now they want us to give them the first non-zero 4 terms, all right, and then the general term. Well, the general term is basically going to be the same, but let's just write it anyway. Okay, so now what we have here, all right, we're going to plug in a 0 for n, and that's going to give us a 1. And the next one is going to give us a 2x, and the next one is going to give us a 4x squared over 2 factorial minus 8x cubed over 3 factorial. So that's all they want from us. Of course, this series will just keep going, right? Is there anything else they want? And then, well, the general term, I guess I should write maybe the general term. General term is basically going to be the same thing as the sum, except for without the sum. Okay, so that's that for that one. Okay, so let's go ahead and move on to the next one. Now, on the next one, they're asking us to use the Maclaurin series that we just found to find the derivative of this. Okay, so we're going to take the derivative of this, which would be normally easier to do without any series whatsoever, but you're going to see that sometimes this will make it easier. Okay, so now we're going to take the derivative of this, all right? So let's see, f prime. I'm trying to figure out a way to write this. So we're trying to take the derivative of this. And we know that's the same thing as taking the derivative of the series that I found on part A. Okay, so now, well, really, and you're going to take the derivative exactly like you would take any other derivative. Just remember that the ends, all right, and the series are not something you're taking the derivative of. Remember, we were taking the derivative with respect to x. So all I'm taking the derivative of is the x values. So this right here would be this. This is not going to change. This is not going to change. On the bottom, the n factorial is not going to change, all right? The only thing that changes is this, that quantity. So I'm going to bring the power down, and then I'm going to subtract 1 from the power, okay? And that is pretty much it. Let me see if there's anything different about this. No, that's pretty much it. So that's that for that, guys. I guess we'll move on from there. So it's your derivative using the series, the Maclaurin series. All right, so let's go ahead and move on to number 2. So now we're going to use several tricks to figure it out. Now, this is sort of, not sort of, it is related to the power series that we did on the last section, okay? Specifically the geometric series. So let me give you some hints or how would you be able to know that, okay? So this is one that I found. I mean, obviously I didn't have any concept of this until about last week, right? But please remember or recall, if you will, that 1 over 1 minus x, which is a power series that works out a lot like a geometric series, is equal to this. All right, so this is kind of a subset of a geometric series. Remember, a geometric series, you had something that said, let me see if I remember, it was like a over 1 minus r, and that was the same thing as the sum as a times r to the n, right? So it's the same idea, or at least in my head, they're so related that I can't really avoid them, right? So, well, how does that help us? Okay, so now what I do know is if I rewrite this like this, and I'm talking about this problem, by the way, right now I'm going on to trying to solve that. If I rewrite that like this, where this right here that I just put in parentheses is the rate, if you will, or in this case is the x right here. So I'm going to write this as t cubed to the nth power, okay? Now, this is almost like that. Notice that I have a 1 here where on the actual problem I have a t. So what I'm going to do here is I'm going to multiply this side times t. I'm going to multiply this side times t, right? Simple as that. So now this is going to give me t over 1 minus t cubed, which is what I need. And this is going to give me, let's see, that'd be t to the 3n times t, right? Well, I can write that as 3n plus, remember, I can write this as an exponent, which is what I'm going to do. I can write it like that. Okay, same thing. Now, it does help to write it like that for what we're doing, right? So now, it says to evaluate the indefinite integral, all right? So we do have to get an answer for this, so let's figure this out. So the easiest thing to do, and I'm sure you can do it. Let's see, how do they want us to do this? Okay, yeah. Well, we can actually just take the antiderivative of this, which hopefully you can agree that this is a lot easier to take the antiderivative of. Oh man, what happened here? Because they're the same thing. All right, so we're just going to add 1 to the power and divide by the same, right? So this is going to be t to the power of 3n plus 2. Right, I added 1 to the power, and then now I'm going to divide by the same power. But remember, this is still a series, right? So let's not forget to write this. all of that plus c, and I'm going to write the c on this side. Okay. And now they're also, so that would be it. If that would be basically everything if the only question was to evaluate the indefinite integrals of power series. But there also wants to know the radius of convergence. All right, so to figure that out, we're going to use the ratio test. And if you remember the ratio test, I don't know if you remember that or not, but I guess I'll write it over here. You basically have the absolute value of, say, an plus 1 over an. So that's basically what I'm doing. And that should go to infinity. I don't know what I wrote 1. The limit as n goes to infinity of an plus 1 over an. All right, so an plus 1 just means that I'm going to add 1 to those powers. Okay, so here we go. And then when I divide by exactly this function right here, then I'm going to keep change flip, and this is going to end up on top, and this is going to end up being on bottom. Let's see. So we'll have to do a little bit of math, just like I've talked about before. We can split this up into t to the power of 3n times t cubed. That's about the only thing you can do with that. And then there's really nothing I can do with 3n plus 3. I guess I can factor out a 3, but trust me when I say that it's not going to help you. And then this right here is 3n plus 2, so nothing can be done there. And this is t to the 3n times t squared. Right, so let's simplify this just a little bit. That's going to cancel this. This is going to cancel all of these, so I end up with just t. So I can rewrite that as the absolute value. Remember, I like to do this. You don't have to necessarily do this. I like to take the t out because that's not relevant to the limit. So I like to take that out. And I'm going to take the limit of this. Now, this is one that's relatively simple because we can use sort of the horizontal asymptote rules, right? So this right here is going to give me 1. This right here is going to be 1. It's going to be Betsy, bottom equals top. This ratio coefficients, which is 3 divided by 3, which is going to be 1. Okay? So now, what does that say? Well, what this says, because this is a geometric series, okay, I know that this has to be less than 1. Okay, so there's my, if I were to write my interval of convergence, which it doesn't ask me to do that, but if it did, I would write it like that. Now, to figure out radius of convergence, there's really 2 ways. And the first way, I didn't really talk about it on the lesson that I talked about radius of convergence. I actually don't remember what lesson that was. But essentially, if you can get it to this, this number right here, which I'm about to write in red, is actually your radius of convergence. Okay. So my radius of convergence is 1. Now, just make sure you're aware that only happened also because I only have 1 variable. If I would have had like a 2t or something like that, then it would be different. Okay, so it's not quite as simple. It's still simple, but not quite as simple. But if not, remember what you do is just figure out the length of this interval. Notice that between -1 and 1, that's 2, and then you divide that by 2. So this is 1. So same idea, right? So I didn't really lie to you last time. I just perhaps gave you a more general way. All right, so let's go on, all right? So when differentiating a Taylor series, just take the derivative term by term, radius of convergence, blah, 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 blah. Okay, so let's just go ahead and do this one, all right? So they give me this example right here, and if I were to take the derivative of this, which is sort of in relation to what we're going to do here, All right, notice that I'm using the same type of, this is the same type of function as what I had up there, right? Which we know is a type of power series. And if you don't know what I'm talking about here. Remember, I used that same thing right there. All right, so now the derivative, well, I can rewrite it like this. And if I were to take the derivative, I would bring the -1 down, 1 minus x, subtract 1 from the power, and then multiply times the derivative of the inside, which is -1. So long story short, this would give me something like this. 1 over 1 minus x squared. Okay? So now, let me switch gears here. So again, this is this right here. Remember, is our good old friendly power series that we know and love. Okay, so here's what we're going to do. Okay, the first thing we're going to do is we're going to try to notice it's going to be a little bit weird. Okay, I can't really just take the derivative of this yet. Hold on, I'm trying to think how they would do this. Okay. All right. So now we're going to find the series first. Okay, so what we're going to do here, knowing that this kind of leads into this, right? Or the other way around, is we're going to, instead of... wait a minute. Here, let me pause here for just a second because I'm a little bit lost on what I wrote there. Okay, so I'm back. So yeah, what we're going to have to do here, and I kind of lost sight of what we're trying to do. We're trying to find a power series for this. Okay, so this is what we're trying to find. And then after that, we're going to find the radius of conversion. So what we're going to do instead is we're going to take a function that by the time I take a derivative, all right, I can actually get really, really close to f of x. All right, so I'm going to take this function right here. And when I take before I take the derivative, I'm going to rewrite it like this. And why do I rewrite it like that? Well, because then this enables me to basically take the derivative of this function right here, except for now the thing that changes is that this is -x. So don't write this down yet. I could rewrite it like that, but I normally choose to write it like this instead. I choose to write it like this. X to the n. All right, so this is what we have, okay? So now, what we're gonna do now, and notice that this is that's gonna basically make it, what do you call it? It's gonna make this an alternating series of some sort, right? So I'm gonna take the derivative of this, and notice that I'm gonna get really close to what I would need, right? I'm gonna do the actual derivative over here of this function right here. Same idea as before, or this function, yeah. So you would have, if f of x, well, let me just say the derivative of 1 plus x to the -1. Right, I bring the -1 down. I subtract 1 from the power, and then I multiply times the derivative of the inside, which is 1. So I'm using a chain rule. So notice that what's going to happen, though, is that I'll almost get what I need, except for I have a -1 over 1 plus x squared. So notice that I'm just manipulating the function here, right? Now, if I take the derivative of this now, same idea. Remember, I'm taking the derivative with respect to x, all right? So please don't touch the n power, like the n. That's not something you do. Like, don't try to take the derivative of this, is what I'm trying to say. Okay, so what I'm going to do here, well, that's just a constant, so I'll leave that alone. Now this is going to be this right here, right? Bring the power down, subtract 1 from the power. All right, so now To make it exactly the same, though, what I can do is I can multiply both sides times that -1. Okay, so this is going to give me 1 over 1 plus x squared, and this side is going to give me the following. Okay, so that's that for that. So I found that power series that I was looking for. Right, so technically that's part of my answer right here. And then now they want me to find the radius of convergence. So for that, I'm going to have to do the ratio test. So similarly to what I did on the previous problem, I'm going to take the limit as n goes to infinity of, add 1 to the n's, right? If I add 1 here, that's going to give me an n minus 1 plus 1, just n, right? Now at this point, guys, you can kind of fast forward. I don't really know if I need to necessarily simplify it for you. I do feel the need to at least do it. So if this is taking a little longer than you want, just go ahead and fast forward, see if you understand how I was able to simplify this. Let's see. This cannot be simplified. This cannot be simplified. Wow, that's a bit of... I miswrote something here, though, fellas. I just realized that. Should have been a 2. And then this right here cannot be simplified. This can, though. All right, so this is obviously going to cancel this. Now, this right here, technically can cancel one of those. But what's going to happen is that this -1 that I have left over, when I take the absolute value of that -1, it's not going to matter. So I'm not even going to write it on the next line, okay? Now, what else cancels out? This x of n's cancel out, and the rest stays there. Now, what happens to this guy right here is x to the -1 can come to the top. Alright, so I'm going to write this as the absolute value of x on the outside. Alright, so again, this x right here is that x that I just wrote. Am I skipping too many steps? Maybe I am. Here. I'll just write it like this. It really doesn't matter. You can keep it inside the absolute value function. I like to not do that, but it's just really a matter of preference, right? So when I take the limit as n goes to infinity, again, by the rules of the horizontal asymptote here, that's just going to be 1. So I'm left with the absolute value of x, and that has to be less than 1. Right, so my radius of convergence is 1. And on this one, I do not have to check the endpoints because this is one of the power series that's related to the geometric series. So as long as this right here is less than 1, then I know it converges. So there's no need for me to check the endpoints. All right, let's go on now. I'm going to try to... And then we have a binomial series, which I actually never done. And honestly, I couldn't even see one on your homework, but nonetheless, I guess I'll cover it. Okay, so now I have 4, 5, and 6. So let's hurry up on this one. All right. So one thing you should know. All right. So this is the one where you are gonna have to do some of these. Okay. So you're gonna have to know. So hopefully we remember, or at least we can look it up, that the derivative of the inverse tangent, all right, from AB calculus, not even from BC, is basically 1 over u, in this case 1 over u squared, excuse me. On the bottom is going to be 1 plus u squared. U is this. So if I square that, I get 4x squared, right? Times the derivative of u. Now, since u is 2x, the derivative of that is 2. So again, if you have any more questions about that, please let me know. Okay, so now let's see what else we need to know at this point. I don't think we need to know anything else besides that to solve the problem, but let me just check my notes. Okay, so what does that mean? Well, what I know is that the antiderivative and this is the reason that I'm doing this, of 4x squared dx is the inverse tangent of 2x plus c. All right, so that's the reason that I'm doing that. So to find the power series, what I can do is, instead of trying to find the power series of a trig function, what I can do is I can try to find the power series of the derivative of it. So you'll see what I'm talking about here, hopefully. So what I'm going to do here is I'm going to take the antiderivative of this, because I know that's the derivative, right, of the inverse tangent. And since we want to know the power series, all right, I'm going to get that 2 out of there for a minute. And this has a nice, a nice, what do you call it? It's basically in a form that we can recognize, all right? This is another power series. So I'm actually going to rewrite it like this. And remember, it's the same thing as what we've been talking about, as 1 minus y minus x, which is, so I'm using the same one that I've used the past couple of times. Is that one, right? Which is related to the geometric series. I think this was a y minus r. Like that. Okay, so it's basically the same thing. So why does that matter? Well, because now, if I just factor out a negative out of here, right, I can make it fit into this form right here, which is really nice for me, because I already know what the series is going to be for that. It's going to be this, right? Where this is kind of like it's R, okay? Now, I can kind of simplify this a little further. Notice that thankfully they're not asking me to find any radius of convergence or anything like that. So all I have to do is I'm gonna simplify just a little bit. I can separate this like this, and I will, because this is gonna make it easier on me. And then now I'm gonna take the antiderivative. Okay, so what I have here, right, before we get too far into what we're doing here, I'm about to find the antiderivative of the inverse tangent of 2x plus c. Nope, and I forgot to write the plus c over here. All right, so this is going to be 2, and to take the antiderivative, just do it with respect to x, right? That's not going to change, so I'm going to leave this alone. I'm going to add 1 to the power up here and divide by the same. And then now you can see that those C's will cancel and I end up with what I need. All right, so this is actually the you can definitely simplify this more than I already am, okay? And I'm pretty on the notes that they did do that, right? They simplify way more, but for our purposes, this is all we need. And as a matter of fact, I dare to say, though I don't know for sure, that if they were to ask something like this on an AP exam, I wouldn't try to simplify it myself. Right, so let's go to the binomial series. And I guess I'm just trying to show you this because I didn't really see one on the homework. Okay, so the binomial series, which I guess it is pretty useful, is this. It's basically if you have something in the form of this, and k is any number where the absolute value is less than 1. Okay, so then it has basically the following. It fits the following series. Okay, so where the radius of convergence is 1. So let me see. Okay. So I can rewrite this like this. 1 plus x to the negative 4. In this case, notice that, again, k is going to be negative 4. So I'm sure that this is much more complicated at some point than what they show me here, but unfortunately, that didn't really give me a whole lot of problems for me to get better at this. So notice I'm just going to really plug it into the formula, guys, and I haven't done this enough for me to know what to do at x to the n. Let's see. So we have, well, I guess that's pretty much it. I'm just going to plug this into the formula. So I have 1 minus 4. And again, I'm talking about this formula. So k is negative 4. X is just x. Plus, then I have a k minus 1. K minus 1 is going to be negative 4 minus 1. So that's going to be negative 5. Over 2 factorial x squared. Who knew? And really, I'm just writing these just to show you how it works, but it didn't really ask us to expand this. So this is k minus 1, which is negative 5, and k minus 2 is negative 6. X cubed all over 3 factorial, and it just keeps going. Or if I were to simplify that, I get 1 minus 4x. Remember, on top here I have 20. 20 divided by 2 factorial is 10. And then right here, remember 3 factorial is 3 times 2 times 1, right? So that's basically 6. So this is going to give me a negative 20 x cubed, and it just keeps going. All right, so let's move on to the next one because I know that I'm going really long, but a lot of your problems are going to be more like you're going to see in example 6. Okay, so on example 6, we're going to try to approximate this, but we already know, hopefully, we already know one of the series that approximates cosine, right? Which I'm going to write on here for just a second here, if I can find it. All right, for cosine, this is one that you must know. Okay. So that's what I'm going to know here. Now notice that we want to approximate that definite integral. Okay, so the first thing we're going to do is we're going to find a power series for y is equal to x cosine of x cubed. Okay, so this is the reason we're doing this. Okay, so first we want to find the power series. And I'm talking about the power series for this. Okay. we have the cosine of x cubed. So really all I'm going to do, and it's very similar to your homework, is I'm going to replace this right here with x cubed. And I'm going to rewrite the series basically exactly the same. Nothing really is going to change except for that x now will become x cubed. So again, please notice I'm writing an x cubed to the power of 2n instead of x to the power of 2n like it was over here. All right. Just to simplify just a little bit. So I guess you know, a lot of it asked me like, when would this be useful? I guess if you're trying to approximate some integral, that's one way to use it. Again, notice that x cubed times 2n is x to the 6n, right? So that's it for that. Now we're gonna multiply, all right, because that's not what we're looking for. We're looking for x times cosine of x cubed, right? So we're gonna multiply by x. So basically, we're going to multiply this by x, and we're going to multiply this by x. Now, when I do that, or I guess this by x also, to make it easier on myself. So what's going to happen here is that finally this is going to be equal to x. So as you probably find out if you actually have been trying to do this, it can become very tedious because you're just writing a lot of stuff, right? So I'm going to multiply this x that was out here. I'm going to go ahead and write it in here. Now when I write it like that, I could simplify it to this. And I would recommend it because it will make your, if you have to take an antiderivative, which I do, combining this x terms probably would be ideal. So at this point, it's not really a matter of preference. It's just going to make my math easier, right? So there's that power series. Now, number 2 is we're going to go ahead and integrate. Now, integrating this wouldn't be that easy, all right? But integrating this is definitely easier, all right? So there's one instance where really doing this series, integrating the series is a lot easier than doing the function. All right, so the integral of this is the same thing as integrating this. All right. Again, I'm writing a lot, but I'm just integrating really at this point. I'm going to add 1 to the power, which is going to be 6n plus 2. And I'm going to divide by 6n plus 2. I'm going to figure that out between 0 and 1. Okay. So I'm going to plug in a 1 for x. So again, as you can tell, I'm just writing a lot of things, but I can really get in very far. And again, all I did was just plug in that 1. That's all I've done. And then we're going to subtract that. Now, if I plug in a 0 here, that's going to give me 0 for the whole thing. All right, so I'm just going to rewrite it like this. Or I'm going to just say minus blah, 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 0, because I don't feel like writing 0 just to tell you that it goes away. All right. So there's the integration part. So now The next part is the part that I did have to look up because I really couldn't remember that. What we're going to do here is we're going to expand this, right? So we're going to try to approximate this to 3 decimal places. So what we do is that we're going to take what we just found, and I'm going to really write what they wrote by the alternating series estimation theorem. The estimate is at most the absolute value of the first unused term. Okay. So basically what we're saying here is if we expand this, and I'm going to have the result here. Now notice that right here, 1 to the power of 6n plus 2, that's not going to change anything. All right, so it doesn't matter. You don't have to write that. As a matter of fact, it would be a waste of your time if you did write it. So this is a series that I came up with on, I guess what I call part 2 of this problem. And if I just expand it a little bit, and you can kind of see, you can take my word for it or not. You can figure this out on your own. I'm hoping to not go above an hour today, fellas. Okay, now it didn't really tell you how far to go, but when you add these up, you get approximately 0.440. Okay, and the theorem, really what this says, the theorem says that if you take this right here, which is the unused term, you would get 0.00007. So it's 4 decimal points. So what they mean by that is that this answer is at the very least accurate to 2 decimal places. Okay, so let's go ahead and don't we have another problem? Is this it? Oh no, this is it. Shoot. I'm fumbling all over the place. Yeah, I believe this is it. Again, guys, homework, it's kind of weird. All right. Please, again, try not to just copy the homework. Try to figure out how to do it. It really did help me a lot. Okay, so, all right, guys, until next time.